Musial, and today we're going to be talking about our journey to implementing machine learning sort of the Kubernetes way at Bloomberg.
Good introduction, Keith, thanks. Just a quick note from the dream team here. So Keith and I are both senior software engineers at Bloomberg with a combined 15 years or so of tenure. And on a daily basis, we work on the same internal data science or machine learning platform, but we do sit in two different parts of engineering, which at least most days encourages a healthy balance of between the minds of distributed computing and the minds of AI researchers. If none of my jokes are funny today, that's because he wrote them. And so just a quick shameless plug at the bottom, if you want to check out a little bit more about Bloomberg data science and kind of what we do, papers we publish, I invite you to look at our blog. So our outline for today looks a little bit like this. Funny? Okay, Keith's joke. Well, that's it, yeah. So we've seen a number of case studies thus far about folks interacting with or kind of building their own data science platform. And today we're here to present you our version of our journey, and we're not quite done yet. But we do have some unique requirements and some fairly sensitive data, which, so using an off-the-shelf solution or kind of a public cloud doesn't quite work for us. But before we get there, the point of the next couple of slides is as much of a shameless plug as it is a motivation for what we've built. And that's that Bloomberg is the best possible place to do machine learning. And this is largely attributed to the types of data sets that we have available, as well as the potential impact that we have. So has anyone here actually used a Bloomberg terminal? You're my product manager, you don't count. Okay. Well, it kind of looks like this. Or at least it did way back when. Back when the company was founded in the 1980s, there's an actual physical terminal, hence the name, which stuck, along with the beautiful, colorful, hand-assembled keyboard that you see here. And the NASDAQ was electronic in the 1970s, and by the 80s, electronic trading was really becoming the norm. So with this, the terminal was really, truly an innovation at the time because it provided unprecedented command line-driven access to market data. So you should really feel an affinity for our users already because what else do you need in life besides, a colorful mechanical keyboard, some keycaps, a nice shell, and some command line-driven like aliases. Yeah. Flash forward to now, it looks a bit more like this. It's technologically evolved quite a bit since then, but it still comes with a fancy keyboard. Nevertheless, the purpose is still largely the same, and it's to provide real-time market data, news, pricing quotes, and analytics as a service. Interestingly, unlike consumer applications or free applications you might be using, the end goal is not about advertising or turning your end-user behavior into a product on its own, but rather to deliver this news, data, and analytics as quickly and correctly as possible. So our users, they'll use this to make fast and effective decisions, typically while selecting portfolios, doing some sort of risk analysis, developing strategies, even executing trades on its electronic trading platform. So typically what happens for an end user, maybe a banker or a trader, they'll choose some sort of stock or bond and they'll start to do some sort of research on it. They might look at its background profile, its description, they might graph its closing price over the past 30 days, maybe even search for it being mentioned in the news. And in order to do this, they load up what we call a function. For those of you with an acute sense of detail, or if you saw Kelsey Hightower's talk this morning, you might realize that it's called a function because it used to actually invoke a Fortran subroutine. But today it's a synonym for like a nice specialized GUI or application. Now the terminal has tens of thousands of these, and they're all very tightly interconnected. So here we have one such function, news trends. And clients really use this to find out which companies or topics are most discussed on Twitter. And they do this by ranking them by the highest volume of related tweets. You can sort these based on the largest spike and also the increase or largest total volume. So I mentioned all these functions are interconnected. And in this case, to provide context for the ranking, there are charts, there's some real-time pricing data, there's a representative tweet on the right-hand side. And each of these cells are kind of linkified to other types of functions on the terminal. So you can really go down the rabbit hole, and all of our users kind of have their own secret special sauce that they care about or signals that they care about when they're making decisions. So just within this one tab of one function, you can kind of already see the potential, right? So within a tweet, we might have a named entity detection and linking pipeline, which could extract this Monsanto plain text and then kind of linkify it to the Monsanto US equity that's on the terminal. To figure out that this is about the topic agricultural chemicals, we have to have some sort of topic classification system. And to detect publication spikes, perhaps we have some sort of statistical model, but now we really get into the realm of anomaly detection. So cool, this gives us an idea about aggregations, but then what about real-time events? Well, if we make the assumption that events move financial instruments or they move securities, then for our users, the question really becomes, how do I figure out which events move which instruments? And how do I figure out the occurrence of events of interest? Does anyone remember the mortgage crisis? Maybe? Okay. Well, here we have a charting function with a timeline of an SEC announcement that was published on their website back in 2010, about 8 years ago. And it was somewhat unusual at the time, so folks really weren't looking at it. The announcement by the SEC here is an enforcement action against a large investment bank during the time, or the actions that they were making during the mortgage crisis. And the price reaction there is actually just precipitated by the Bloomberg headline that was simply reiterating that this announcement had been made. The New York Times is in this picture only to show that commodity news, or news that most people actually read, rarely, if ever, moves the markets because it's typically seconds, minutes, or hours late. And news that most headlines that have direct market impact are actually from subscription news, such as that which is provided by the Bloomberg Terminal. So from an engineering standpoint, the question here really becomes, what kind of tools do we have at our disposal in order to kind of automate this and make it provide this as quickly as possible? In a slightly more modern take, this is the impact of social media, our favorite cesspool of rumors and unvetted events that has the potential for gaining a serious advantage. And this really happened. A mistake tweet on the AP Wire about an explosion that caused Barack Obama to be injured caused the market to react really sharply and quickly. The point here is really just to get across how much potential market impact there is, or how much money there is at stake if you have a bug in your software. So I've given you a few examples or applications that we have. Many of them are in text processing, but it doesn't really stop there. The possibilities are infinite, and it really stems from the types of data that we have available. So we have plenty of image processing problems, ranging from extracting tables, from press releases to geospatial data with live shipping routes, crossed with oil rigs, crossed with weather patterns that might hit them. Anomaly detection we saw, but it also comes in other flavors, such as monitoring all of the backend systems that we have that actually power the terminal. There's an entire world of risk modeling or forecasting. We get hundreds of billions of ticks a day, as well as other types of events that we saw. Audio-wise, we have many transcriptions we can make from, let's say, earnings calls. And there's a wealth of information retrieval problems, such as those within the search, relevancy and ranking domains. And between the two pictures of those terminals I saw you at the very beginning, the time to price in information has really gotten much shorter due to automation, and markets have gotten a lot more efficient, and their users and their expectations are really getting much more sophisticated. So the interleaving of any of these types of data sets really becomes a powerful necessity. So let's suppose a product manager at Bloomberg posits a new feature, and a machine learning practitioner is tasked with finding a solution or developing a model that falls within one of these tasks. So these are the kinds of questions they should spend the majority of their time really thinking about. So one, what is the data that's relevant to my business problem? Do I need 2 years of tweets? Do I need ticks from the S&P? What does my data look like? What formats are the timestamps? Cross my fingers for ISO 8601. What features can I glean from this data, and can I count on them being consistent in production? What metrics should I use to measure success? What am I maximizing, or what am I minimizing? What types of algorithms are most suitable for this problem, and how should I kind of tune or tweak them? And once it's deployed, when is it appropriate to update my model such that the live data isn't drifting too much from my original training set? So you've probably noticed here that there's an implicit assumption that whatever infrastructure you need to kind of answer these questions is readily available. And these are really kind of what questions, right? But ultimately, the efficiency of your work and the accuracy of your model really depends on what tools you have available. So dealing with this how kind of takes up too much of the time. So in an ideal world, to tighten up this sort of model development lifecycle that we've outlined here, these are our requirements. And I've broken these down into a couple different categories, and I'll fill the bullet points in a minute. But compute-wise, experiments are very power-hungry. They're very bursty and seasonal in nature. They require on-demand specialized hardware, and very resource-hungry. In terms of data liquidity, the notion of data provenance, kind of where it came from, how it moves through the fabric of time, is really crucial for debugging and other sorts of model forensics. This typically will come off as, I need access to everything in a perfect format with no errors, snapshotted for all of time, and then a separate copy for each of my experiments would be perfect. And on the right here, a very broad category, I'm terming machine learning workflow or kind of ease of use. It's as much as about the developer experience as it is about scientific reproducibility if you want to actually ship any of your models to production. So let's fill in some bullet points. We have toolkits, we have experiment management, we have zero network overhead, et cetera. And it actually looks quite demanding and verbose, and there are too many things in here, so we can just look at the slides later. But I'll point out one thing that I have listed that's under there somewhere. You may have seen it in some other case studies. But it's the notion of hyperparameter tuning. So these are parameters that are not necessarily learned or produced as the result of training your model, but rather something that you provide as an input or a configuration to your training process. So for example, what's the maximum possible height of my decision tree? Or if I wanted to run the same set of experiments, give me all of them with a neural network with 2 layers as opposed to 3. So if this sounds just like a configuration for a process, that's because it is. You have a suite of deployments, each with a different set of parameters, trying to find the optimal set for which will give you the best results for your data when your process completes. So it's worthwhile way to squeeze performance out, and it's almost free in a sense as long as you structure your code properly, which we don't always do. But the heavier your computation, the more clever you have to be about how you schedule these sort of workloads, because a grid search is not always feasible. So clearly this mess isn't ideal, and with some sort of infinite amount of time and resources, maybe it would be possible, but life is short, and so is headcount. So to make an honest attempt at achieving nirvana will require the collaboration of just more than just beyond the ML practitioners. And so in particular, these are kind of what I see as our stakeholders. We're trying to keep all of them at least happy enough, and they all have kind of different priorities that sometimes come in conflict with each other. So the ML folks that we just saw with their wonderful demands. There's DevOps, like James, whose ideal world is the complete separation of application and hardware. There's infrastructure engineers like Keith, who want to provide a robust generic solution and not have any compromises. There's product managers who are like, how much does this cost, and can you just get this done for me yesterday? That was Keith's joke, you didn't laugh? Okay. And if you deal with any sort of sensitive data, which in our domain we definitely do, there are security officers that have to be involved at kind of every step of the process. When we want to, let's say, integrate new policies into a mature network at Bloomberg, figure out an appropriate data permissioning model or standards, as well as be part of reviews for situations such as, am I even allowed to export this model into production? And of course, we can't forget the wonderful people who actually pay for what we're doing, for whom privacy and 24/7 uptime is a serious priority. So we all have to come together to some sort of managed solution, grand social experiment, if you will. And so with that, what was everyone's emotional state before we began working on this thing? I'm not going to call this failures, but rather kind of prior work or market research or kind of legacy code or things that are still making money. So when I first started at Bloomberg, eons ago, there were a handful of people that were just sitting in my row, kind of experimenting with machine learning within the core news infrastructure team. And that has since grown into an entire organization. So company-wise, we have teams that are dedicated to building a very sophisticated NLP platform, as you kind of saw, as well as information retrieval teams that specialize in building models into search systems. Shout out if you follow Learning to Rank and Solar, if you follow that community. And I should note that they don't just write up notebooks and toss models over the wall. That's not what we do, but we kind of take pride in ownership of the entire software development lifecycle, which is a little bit different than other places. So back then, when I started and these rules-based systems were really kind of turning into machine learning-based systems, the ML-based systems really grown out of extensions of existing applications. It's not really new. It's how information extraction has been done everywhere, but you have a giant rule set or grammar that you just deploy with your monolithic service. So enter our first status report. And the first 3 columns should look like fairly familiar, but the fourth one kind of represents the support teams or the stakeholders, or even lack thereof in some cases. So our data was much smaller. Compute was really limited to our service-oriented architecture and the routing that we had. Hyperparameter tuning that I mentioned earlier wasn't really being done by too many teams due to limitations in how their systems were set up. So it got as sophisticated as kind of spawning lots of threads in C++, maybe import multiprocessing, or if you're feeling cheeky, maybe SSH to a bunch of other machines and you rsync your data around. Interestingly, the development environment from 10 to 15 years prior was not really segregated from your execution environment, but the mindset was really that your code, your executable, your labeled data, and your editor kind of all lived on the same box. And so all this really showed in the types of tool sets that people kind of created and that were built for the machine learning workflow. And these weren't really reusable by other application teams that had wildly different stacks or kind of hardware. So the teams were really their own support. Fast forward a little bit, at some point, like many other companies, big data era rolled around. And this wasn't really a replacement, right, but rather kind of grew alongside the other role, because we have to keep maintaining these systems. So we built up a giant data lake in HDFS, but given the sensitivity of the data there, it's very highly secured. So it's useful if your application's kind of contained, but sometimes you have to grok for some sort of other parts for your model. What about the data that's not there? We also made this a platform for compute, but the combination of this data lake and the compute was kind of difficult to use. We did get more powerful distributed systems, which was great for heavy pre-processing using MapReduce and then later Spark. Spark ML was fairly easy to get started with if you had Spark kind of working already, but it was quite limiting, so you'd always find yourself kind of reaching for these other toolkits that you had started using before, which were a little bit difficult to install because you're subject to kind of cluster-wide dependencies. If you were lucky enough to get them installed there, then you had to kind of figure out how to reliably get them working with various security and authentication protocols, which is always a wonderful joy, especially for long-running jobs like for machine learning workflows. These typically kind of ran under Yarn. Support-wise, having a Hadoop platform team was really nice, though not every use case on that compute platform was really ML-specific there. So their expertise was really well-suited for classical distributed systems problems, and less so. I can't tell when my topic model is spitting out completely outrageous values. Is it because of how Spark is set up, or is my machine learning code kind of full of bugs? So at some point, neural networks kind of became the top performing class of models in many domains of machine learning. And we wanted to support various specialist groups at Bloomberg to explore their use. And this happened very organically, the same way that not every business problem is suitable for a machine learning approach. Not every machine learning problem should be solved by using neural networks. So we gave access to an interactive GPU farm to established AI experts within Bloomberg Engineering to kind of assess their practicality for the types of problems that we were working on. So having built up many wonderful data sets in the past couple of eras, this became yet another exercise in data Olympics, right? We had access to blazing hardware. In some ways, this was kind of a minor setback to our rules-based era where folks would really step on each other's toes, but only this time it was on much more expensive hardware. And we got some isolation by running in containers. We began to, which were also really useful for kind of installing the latest neural network packages. But going back to practicality and scheduling, what about ETL? Now we have kind of folks that are kludging together pipelines between vastly different environments because pre or post-processing really happens on your own servers or maybe within Hadoop. So support-wise, all sorts of questions come up. Why did this machine blow up? Why is this SRE killing my notebook? Can someone get the latest TensorFlow drivers installed? And so on. So looks like leading up to this, we've identified a few different things. One, there are some fairly peculiar types of workloads that machine learning world requires. And based on the limitations of the previous systems I just talked about, this needs to have some serious thought put up front in regards to data liquidity, proper multi-tenancy, and really stability. And up until now, there have really been kind of ad hoc solutions for each of these. So it was becoming clear that Kubernetes was the winner in the community, at least with regards to scheduling, and it would lay the groundwork for a lot of the different aspects that we need.
This is when I enter from stage left, but I think this is actually stage right.
Yeah.
So, all right. So as Ania mentioned before, our prior work, or whatever you wanted to call them, included three sort of themes: a single node workload, the sort of distributed workload around lots of data, and then GPU-based workloads. But we wanted one way to encapsulate all three of these together while providing a pathway for users to choose any of them without having to reinvent the wheel each time like they were sort of doing before. So we chose Kubernetes to help. So when we chose Kubernetes, it was because it offered all the abstractions we needed to build the platform that we wanted to build and deploy and run these processes in a way that we can utilize compute much easier. So there was jobs and pods and deployments and so on. And these are all like declarative ways to specify your application, but in a kind of abstract way. We've kind of found these abstractions to be a little too abstract. So we wanted a way to make them better support ML workflows while also being declarative and reproducible like the rest of Kubernetes types are. So lucky for us and Kubernetes in the community, about 3 years ago, there was something called third-party resources. And then later, they became custom resources. And now everything is custom resources, of course. And so now you can define your own types, and you can use those to build whatever features you want into Kubernetes. And we did that to make ML-specific types while utilizing the abstractions that Kubernetes already offers. So to get an idea of our philosophies and base archetypes, we'll take a look at some of our basic custom resources. And the first one we'll look at, it's called our TensorFlowjob. So from early on, if we're looking at the spec, we wanted to own this concept called frameworks. So instead of ML practitioners having to learn Docker and losing focus on the job at hand, they can just require one of our managed frameworks. And we built a bunch for the most common languages and toolkits for data scientists. So you require a baseline environment like this, TensorFlow 1.7 Python 3. And then we can own the base operating system, set any sort of internal proxies, configurations that we need, and make sure all the drivers are set up right. And so ML folks don't have to think about that. And now, because people don't create their own Docker images, they need some way to get their runtime dependencies into the base framework. And so they can do that by specifying their pip packages and the module they want to become their entry point. And it's been interesting, because this paradigm has sort of been becoming a little bit more popular with the serverless style frameworks, where you have this base framework and then a set of dependencies you want to be pre-built into your image. Next theme was data, and we wanted to make that as easy as possible. So we made data a first-class citizen into our resource type. And we did that by creating a concept called identities. And identities can be thought of as a sort of managed secret config map combo, where when you specify an identity, specifically this Hadoop identity, we'll make sure all of your tokens and token renewal happens autonomously behind the scenes, and we'll mount all those configs that you need into your pod at runtime. And so you don't really have to think about the security model of Hadoop. You just sort of specify your identity, and assuming you have the permissions for it, it just kind of gets loaded in for you. So now, as you create other types of jobs, you just add this identity in, and it kind of can just follow, your data just kind of follows you around. The next concept we came up with was the size parameter. We needed a way to switch between CPUs and GPU-based hardware. We also didn't want people to have to think about specifically the amount of memory and CPUs they needed for the job they were running. So instead, they can think about maybe the amount of data they were trying to crunch and choose a small, medium, large sort of t-shirt size and specify here with also the CPU, GPU prefix to hint to the scheduler what they need for hardware. And if this doesn't work and you need to go deeper, we do have custom sizing for specific request limits. And this last bit here is just for the arguments that get passed to the application. Here you can see they're going to use the Hadoop identity, which was specified earlier. So we've taken this a step further and extended it to multiple different types of CRDs in order to satisfy all of the themes from earlier. We have Python and JVM jobs to provide an appropriate base framework for many of the other common data science choices. We have a Spark job for our big data ETL style pipelines, and then the TensorFlowjob, which we talked about, and a meta job for hyperparameter tuning, which is something Ania sort of alluded to earlier. And this job takes as a template all of our other types of jobs and basically schedules a black box hyperparameter tuning cycle over your parameter space. So setting all of this up has really given us a good groundwork framework for onboarding individuals and to scale for more people and sort of allow our ML folks to think about ML without having to think about compute specifically. So at this point, we sort of have parity in this data column with our previous iterations, HDFS, S3, and various other data sources. We've also combined almost everything from the big data world and the GPU world in terms of compute, while at the same time making it more ML specific and declarative by introducing native Kubernetes CRDs. And with using CRDs, we can sort of now split out what ML practitioners care about and operational teams care about because we have Kubernetes scheduling it. So that's the end, right? Everything's good, everyone loves it, and we have a full ML platform. Not exactly, right? It's hard to convince a bunch of people to move off of the workflow that they were doing and deal with some unfamiliar platform that maybe isn't even full-featured yet. So some of these folks were, before having exclusive access to maybe their own team server, VM, which had like a quick feedback loop, toolkits they're familiar with, like native Unix CLIs, and now we want them to move to the cloud and use tools they've never used before to debug, which maybe feels like they're debugging in a black box. Additionally, straight porting things like things that run in a JVM or use Python multiprocessing, if those weren't running in containers before, you might notice there's some different interesting behaviors when you try to move into a container environment. And from an infrastructure perspective, when we started, we really wanted to build something that could be injected into this MDLC, model development lifecycle, in the way that a software development lifecycle works. We wanted to enforce our best software development practices on that. But that doesn't always necessarily lead to the best ease of use. So now we're at this sort of crossroad where we need to think about what do we need to add to make the user's experience more graceful, but without compromising all of our best practices. So just to recap, when you had this server or VM or development environment set up, you have a REPL, or maybe even a local Jupyter notebook. So now we want to bring that interactivity to the cloud. And so the first thing we did was expose a Jupyter job, which I'm sure many people are familiar with. And it's also sort of a hot topic in the community about how it should be presented to people. But we wanted to give people the same sort of experience as using one of our Python jobs or JVM jobs, in the way that your identities and package management can follow you into your Jupyter notebook. So now people can sort of switch between the two, but explore their data shapes in a more interactive model. So we also wanted people to do some local development to test the sanity of their code, but if you don't have the data accessed locally, then you sort of have to move into this Jupyter environment. Additionally, we've given the ability to kube-control exec, which has eased some of the debugging issues off of infrastructure folks to help out and empowered our users to do that themselves. And we've also put a lot of effort into building a friendly UI, which unfortunately is not pictured here, but it allows our users to explore their job history logs, and it's really a jumping off point to a lot of tutorials and documentation. And this, coupled with a lot of education about how the sort of cloudy paradigm works, has made people a lot more comfortable with switching over. So things are starting to look up a little bit for ML practitioners, but with every new bit of power given to users, we have to worry about how that power is going to be abused from the infrastructure side. So in this case, all those greedy interactive users are probably going to be clogging up our resources and locking GPUs and CPUs, right? So now we sort of get to some better problems. In the past, we just wanted to get people on the platform, but we had no people, so we don't have to worry about scale, and we just kind of were able to build something. But now everyone's using it, people are using interactive. We need to figure out how to make it fair for everybody. So the question now is, how do you make users care about sharing this Kubernetes cluster? And well, we're doing that by forcing it with infrastructure. So first thing, you want to create a namespace, and this is something we did from the start. Every user gets their own namespace, and namespaces obviously can have resource and security benefits. And we knew there was going to be a lot of things that we were going to add into the namespace, so we created this higher level concept called a workspace. And a workspace is basically just another CRD, which defines all these things you see here. Right, so it was sort of interesting because in the beginning we wanted to get, it was all about like user adoption, right? So we sort of had this small cluster that we can foot the bill for, and other teams didn't really have to worry about getting budget to join into our platform. But that didn't really allow us to give production level SLAs because we can never guarantee we'd have capacity to schedule, right? But now people are getting comfortable with it. They want to join. They want to use the platform we've built. So we need to figure out how we can sell it to them. So we split it out into sort of 2 different tiers. We have this user tier, which is more for developing and testing and has lower priorities for scheduling, and then a shared workspace, which you pay for with a budget, and then you sort of get a resource quota limit, but a much higher priority during schedule time. So now all the squatters we were worried about can sort of still squat, but at least they're paying for it. And another small addition we've added was deadlines to our CRDs in the way that jobs and pods already support deadlines. So now we can sort of impose this onto the free tier if we want to. So again, we lend with some trade-offs, though. One of the best things about using a cloud is the ability for over-provisioning on your hardware or compute. But if you want to support both a production level SLA and easy onboarding with this sort of low priority, it might schedule at some point tier, you need to sort of introduce this idea of preemption now. And some applications like TensorFlow, Spark a little bit, Jupyter a little bit, have this ability for checkpointing built into it, but the more naive toolkits maybe don't have that, and it needs to be added or adopted, which is going to be now another challenge that ML practitioners are going to have to face. But on the other hand, we can guarantee better SLAs because we no longer have to worry about specific resource questions and squatters and so on, because it's sort of built into the system now. So now that we've made the cloud a little bit easier for users and we've given them access to compute, we need to remember that we're still building a full-featured ML platform, and that's only part of the story, right? So let's just talk about some other features we've been thinking about and adding into the platform. The first one is a history store. So, you know, kubecontrol is great, and Kubernetes is great for getting the jobs which you've submitted, but if you have multiple clusters or many, many jobs, etcd might not scale the way you want it to. So we've taken that and put it into a separate database, which allows us to tag and annotate jobs so you can sort of look at multiple runs of a trial together and aggregate them after the fact of running them in Kubernetes. We've also been adding features to collect metrics and performance information from the models which you've built. And so we've really been able to roll this into a full model development lifecycle workflow. So if we look at the status report again, now we're basically just adding features to our ML workflow. So continuing on that trend, we need a couple of more features that a full platform should have. So up until now, we've talked a lot about training a model and other types of data science and manipulation that might actually not necessarily end up with a model as the output. But if you are training a model, you probably want to serve some predictions with that model, right? So at Bloomberg, we actually have a bunch of different ways to deploy applications, which in turn can be used to deploy a model prediction service. But you might be doing inference in some other ways as well. So Ania before mentioned Solr's learning to rank, which is basically a prediction serving service that lives inside of the Solr search engine itself. And so if you're training on our platform, you're going to have to go and move to another ecosystem to do that anyway. But a lot of people want the seamless way to go from training to serving and don't need anything too specialized. So it's a great candidate for a full-featured platform. And so right now we're working on Knative to build model-to-serve Lambda pipelines. And then once that exists, we can sort of integrate other ML-focused tools that already exist at Bloomberg directly into this model lifecycle, like our annotation platform, which allows you to collect judgments and labels for your data set, and then we can automatically retrain on the platform, redeploy, retag our models. So we're also doing a little bit more work on the distributed side of things. We're working on Spark native Kubernetes scheduling, so much in the way that Spark currently uses Yarn to schedule and scale its workloads. Some of our folks are working on bringing that to Kubernetes. So just to tie this all together, Bloomberg has 6,000 engineers, so really it's an engineering company at heart with a huge wealth of data available. So to allow our engineers to build products utilizing this information quickly and efficiently, we really need to simplify all of the roles involved. And so with Kubernetes and the data science platform, which we've been building, we've been able to split those roles up between infrastructure and ML specific. So thank you all for coming out to the talk. We had a couple of other presentations from Bloomberg. I think they've all happened already, and if you haven't seen them, you can see them online. And if you want to be my teammate, you could click on that link. And I don't think we have time for questions, so I will meet anyone that wants to talk on the side over here. Thank you.